It's been a while since I've put together a system design interview, so I've been just kind of busy and interviewing recently, and I got a tech leadership role in my team, so I've been working on that. So sorry I haven't had a lot of time to put together a video, but I figured I would put together a video about and a question that I got pretty recently that might be interesting for people. So this was for a company in the financial sector space, and they wanted me to design an online brokerage system. So what this system did and how to approach this kind of question if you were to receive this in an interview is first always ask for what are the requirements of the system. So the requirements are online brokerage system. Gathering the requirements is really similar to doing any sort of like tech leadership in a big company. You have to understand what you're building in order to build it properly. So the brokerage system will need to be able to feed prices real time to a list of consumers. It will also need to have a historic price data API. So that means this service needs to have the ability to retrieve data between like a set amount of days for a specific ticker. So now that we have this kind of requirements, we can always start with building the backend. So every system will need a backend, and this backend could be built on something fast. So you'd probably want like a Java, a Go, a C++ backend for handling our requests. Since it's streaming real time, we would need some sort of real-time price oracle service. So this price oracle will have the ability to get real-time updates of prices. And the price oracle will need to hook up to some sort of outside data source. So whether this is something like the NASDAQ, maybe like the New York Stock Exchange, each of these services need to hook up to our price oracle, and these services will push updates to our oracle as they come. So that way our oracle will always have the most updated price, and from here we can feed it into our backend. So since this server will likely need to handle a lot of requests, one good question to ask at this point is, how many requests can we serve? And this is very important because this will decide whether we scale the server horizontally or vertically. So the difference between horizontal scaling and vertical scaling is horizontal scaling scales with number of hosts instead of and opposed to something like vertical scaling, which scales with resources per host. So this is the type of scaling that is differentiated between systems that have many hosts that do a very simple operation versus a system that performs a very complex set of instructions, but the host itself don't increase in number. So something like an order book would be vertically scaled, but something that does that pushes updates could be horizontally scaled. So by horizontally scaling it, we could have a set of services that that will serve the clients. And since, let's say we also need to know how many hosts we need to provision for this, let's say like each host can handle around 50K requests per host. So we would take the number of requests divided by 50K, and that will give us the total number of hosts that our auto-scaling group will need at a maximum. So now let's talk more about how a API request reaches the backend. So here, since we have multiple hosts, we need some sort of load balancer in order to route the client request to the correct host. And this load balancer will take a request and send it along to our backend. And load balancer will be able to connect to a client. Let's make it a person. So the client hooks up to the load balancer, and once the client is synced, then the load balancer will push updates to the client for a specific ticker. So now this is an important distinction to make. How will we create an API call, and how will we know what data to push to the client? And another consideration to have is, what will the client need to retrieve all of the tickers or only a subset? And will the client need to pull or do some sort of pub sub synchronization? So since this is a real-time brokerage system, we could do something like pub sub, which is much more versatile than something like polling. So pub sub stands for publisher subscriber, and this is done over something like WebSockets. So the publisher will make one connection to the server, and then as the load balancer receives requests and responses for the client, then it'll push those updates to the client. So designing an API like this can look something like this. So subscribe, and we could create a set of product IDs, which is an array of strings, and as product IDs get retrieved from the price oracle, then this will get pushed to the backend, which will send it to the load balancer and return it to the client that is listening for that product ID. So a sample request that could be sent, and I am struggling with the drawing tool here. There we go. Let's say the client creates a subscription for Apple. Now a product ID of Apple is sent to the backend. Let's say 165.65. That data is sent to the backend. Then it will get returned to the client using the keep alive connection created during the subscribe call. So this would be the return data. Not for the subscribe call, but for the keep alive connection. Cool. So now we have some sort of process that is able to maintain connections to the clients, and also a call that lets the load balancer know what kind of ticker data needs to get sent to each client. So the question is, how do we store this kind of information on a load balancer? So since we can't, since it would be hard for one load balancer to create, it's hard for one load balancer to maintain all the connections to every client, we could create a subset of pub sub senders. And then this is what the client is actually subscribed to, while the load balancer would use some sort of consistent hashing in order to know which pub sub subscriber it should send to. So it would send the subscribe signal to the load balancer, but the connection would be created with the pub sub handler. And the load balancer would send it to the correct pub sub handler. So now that we have this data, we would also need some sort of way of caching which sender is which subscription belongs to which sender. So we can use a data store similar to Redis, or we can use Redis for this exact use case. And in the Redis store, we could have an IP address that maps to a pub sub sender. And this pub sub sender could just be an ID of the internal address of the pub sub sender. So before the load balancer actually retrieves it, it would get the pub sub sender from the Redis store. The Redis store would return the sender ID, and then the load balancer would reroute the connection to the pub sub sender. And then the pub sub sender would maintain a connection to the client. So now we also need some sort of way of notifying the pub sub senders from the backend when a new update is created. So here we can use a SNS topic, which is which is a way of transmitting messages, and multiple pub sub senders can subscribe to an SNS. So each ticker could become an SNS topic. So when Apple is ticked, then send updates to pub sub senders and return a new ticker update to the client. So now we should also format this sort of API response, and we could use something like a JSON. So let's say for subscribe, they subscribe to Apple, and then when an Apple tick event happens, the JSON could look something like this. So now this is the data that's being returned to the client over here. Cool. So it looks like we have most of the real-time system in place. The pub sub senders can scale to as many clients as we need. Let's say like each pub sub sender can handle 10K requests per sender. And then that means we would need, under maximum load, we would need around number of requests divided by 10K equals number of hosts. Cool. So now we figured out this scaling problem that we had. The SNS topics will scale. Since we're using AWS technologies, we don't have to manage that. Otherwise, we could also use like a Kafka messaging queue to send the updates to the pub sub senders, and every ticker could become a topic. So in addition to this, we want to also create some sort of caching system in order to store these ticker events. So for the sake of simplicity, we could create a data store with Postgres. And in addition to sending the data to our backend, the price oracle will send it to our database. And this can be done either by a direct request or also just some sort of SNS messaging queue or SQS messaging queue. So update data in data warehouse. And then this will lead us to our next section of this question, which is designing the historical price API. Before we do that, let's just define a schema in order to understand how this information is stored. So information that could be on this is the ticker ID, the ticker ID, which is a varchar, the price, which is a decimal, the created at, which is a timestamp, and that would be most of the information that we need per price update. We could do more complicated stuff via ETLs, but that is beyond the scope of this question. So now we need to create the historical price API. So for the historical price API, we would need to reference some of the information for our preliminary data warehouse that we haven't finished yet. But to start out, let's just go ahead and define the price API, since this is something that is going to be much lower transactions per second. So let's do get prices, and let's call it with product ID, which is a ticker, the start time, which is a timestamp, end time, which is a timestamp, and the granularity, which is a enum. So this means that a sample request could be something like ticker ID, which is Apple, and then a epoch timestamp, let's say this. I'm gonna make something up, and then an enum, which is minute granularity. So this will get all of the prices to the minute for that ticker between the start time and end time. So now that we have defined an API for this, let's go ahead and create the backend system. So we can really expand on what we already created here, and we can create a backend. Let's build it on Java. Go or C++ again. Of course, this is actually something we could also do in Python since it's not very high throughput. It doesn't have to be very fast. So we also need multiple backends in order to handle a large influx of requests because we don't want any downtime to the system. And let's create another load balancer because we will need it to handle multiple hosts. Now, let's say a client calls this load balancer. Let's make another client just to make this easier for us. Let's say this client calls this load balancer. He calls it with the historical price API. And then the backend will need to go into our data warehouse in order to fetch the data. So let's say the latency for this request is 1 to 2 seconds. We want this to be as fast as possible. When we get the data warehouse, if they hypothetically pick like a request that was like by the day between like a huge start and huge end, this request will take time, especially if we're looking at the event-based granularity, because we would have to do some processing. We would want to create some sort of ETL system in order to handle rolling up the data into something that makes sense. So this ETL system will work repeatedly on the database in order to roll up data into the different granularities that we support. So this granularities could be minute, 5 minutes, 15 minutes, 1 hour, 1 day, 30 days, 1 year. So let's say these are the granularity sets that we support. We would want to create an ETL that will roll up this data, and then let's say like we could make the format of the data similar to start ID of events, end ID of events, ticker ID, and then just some interesting price data like start price, end price, volatility, volume, etc. So this will be an integer, this will be an integer, this will be a string, this will be a times, this will be a decimal volume, and then this will be an integer. And then let's do a created at date, which is a timestamp. Cool. So each granularity will be a different table. Yada, yada, yada. And this will be rolled up, and then we can run this ETL once every minute. And then the ETL basically will perform a query that gets this kind of rolled up data and then outputs it in this format and inserts it back into the database. So now once we get a query, we can write a SQL query, something like this. Select all from ticker data granularity, and then we can replace the granularity with whatever we want. And then let's just say greater than where created at between start time and end time, and then return whatever data is returned from here. So now that we have this data, the question is, should we have it allow it to interact directly with the database? Typically, I think that it makes sense to have some sort of data access layer, because since we want this service to run in like 1 to 3 seconds, we want as much data cache as possible. So let's create a data access layer, and then this data access layer will interact with a cache. Let's say Redis again. And then it will check Redis, and then if not in Redis access database, then store in Redis. So we should also take into account what the key will be. So let's say if the key is ticker ID and the start time, end time with the granularity. And then the value will be a blob of that information. So there's two ways of caching it. We could cache the individual dates for each granularity, or we could just store the entire query. I think it makes sense to store each one, and then we can do repeated multiple cache calls in order to get a larger time range. That way we're able to cache more data per run, and also have a way of retrieving it, because hypothetically, if we had multiple requests that were something like this, 0 to 100, then if we store it the first way, this is one giant blob. And then if we get another request that was 0 to 90, then we wouldn't be able to access this blob. However, if we were to store each one as a minute granularity, then we can do 0, 1, and then that's a blob. And then we can do minute 2, which is also a blob, and then we can just query the entire Redis cache in order to get all of that data. So now, once we have this information, we can return it in this call and return it as an array of JSON data, which is the parsed version of this schema. So day 1, day 2, yeah, etc., etc., etc. So that's how we would create this historic price API functionality. Let's say that each server can handle about 50K requests. That means we need number of requests divided by 50K in order to get the number of hosts. The ETL, we are operating on the single database, so we could have multiple ETLs running if it causes a slowdown, and then assign different workloads to each one. We can have some sort of job queue in order to do that. Redis is single processor, so Redis scales vertically instead of horizontally, so we can only have one Redis server. We have the real-time server, real-time price feed setup. So I don't think we need to create any more changes here. But overall, this would be a very good way of approaching this kind of system. So another thing you could focus on to showcase your knowledge here is what kind of database system. So we could use Postgres here, which is a very standard format. We could also use something like Dynamo, which is eventually consistent, or something like an analytical data store, which is column-based instead of row-based. These are all good options for picking a database. We could ask if we should introduce sharding, and on which key should we shard. We should also consider the storage constraints of this. So integers are 4 bytes each. So overall, this schema per ETL is 4 for, this is varchar, so like around 10. Decimal is variable depending on how many decimal places, but let's just say it's like 10 per, this is 4, and timestamp is 4. So this one is about 16, 30, 46 bytes per row. So we also need to consider the raw data, which comes out to, let's say like 10 plus 10 plus 4. That comes out to 24 bytes per row. So this is 4, let's say 10, sorry, 10, and then 4. Okay, so it comes out to 24 bytes per row. So this should be able to handle a lot of items, and then maybe if this expands past like our storage needs, we could offload everything into an S3 bucket and then clear the database, which is another option. Or we can use a modern resource like maybe like Snowflake or Redshift. The New York Stock Exchange is not part of our system. We just have to listen for price updates. Our API looks good. PubSub senders, load balancer, Redis store. Yeah, overall, this is how I would approach this online brokerage system. And this is a good approach to how to build this. We would need something important to note for your system design interview. I would always consider horizontal or vertical scaling and whether to introduce a load balancer. Question like what kind of databases to use, how do you get data to the user, how do you define the API for the user, as well as creating different layers. If something seems too complicated, always you can make a new layer. Overall, yeah, this is my approach. Thank you for watching, and like and subscribe if you like these videos down below. Hit the red box. It really helps me get my subscribers up. I'm working on getting 1,000 subscribers for the YouTube creator program. So hit that like button and hit that subscribe button. It really helps me out. Thanks for watching. Comment below on what kind of system design interviews you want, whether I should focus on more system design or coding. And as always, much love. Thanks again. I had a great time teaching you, and peace.